All right, I have 26 clicks. I think we have more people than that. So go ahead and read this question. We're talking about a reaction specifically in the direction that is shown. We're talking about standard enthalpy of atomic combination being shown here from the worksheet, the packet that I gave you last week. On the right side, enthalpy of formation. Totally different values. Does this look familiar at all? You guys find values that didn't match over the weekend when you're trying to do your homework? The last question? Okay. So go ahead and click in your responses. So let's go ahead. We're split almost 30-30-30. So let's go ahead. I want you to tell me, I want you to calculate the enthalpy of the reaction of O2 going to 2O. Go ahead and calculate that. I'm going to close this clicker. I'm going to open it as a numeric or alphanumeric. Let's click in what the, let's use these values. Let's use the OWL values. Centigrade, and what is the delta H of the reaction using the values on the right? You might want to draw your little diagram, what it's starting at, what it's going to, what the value of each is, that kind of thing. All right, we only have 15 responses. So I want you to calculate for both. I want you to click in delta H using the values on the right. Because we're going to look at whether this affects your values. Which of these sets we use? It affects your calculations. You're still trying to answer that question, but you're clicking into the right side here. What is delta H for the reaction as drawn? Values on the right. No, the answer is not A. No, the answer is not A. No, I mean someone typed in A for their short response, and I'm saying A is a submitted response for this is inappropriate. It's like some people just submit one. Geofencing not working? Yeah. So, Eric, were you able to fix that? So close the app, make sure you're connected to Wi-Fi, wait for 1 minute, and then connect again. I'm guessing it's just like it needs to sync and it still thinks you're outside or something, I'm not sure. Alright. First thing I want you guys to do when thinking about a problem like this is actually picture the energy diagram. So are we starting at lower energy or higher energy? Which one's more stable of these two? O2. We're going to do the one response per day. So you just chose your one? Yep. All right. So why is this one, you get one more. Why is this one more stable? Why is O2 more stable than O? How do we know that? Why can we say that? Savannah?
Because O isn't like naturally like that. It was like ripped from the whole molecule.
Okay, great. So I like you're visualizing that this process is a ripping apart. If we have O by itself, it doesn't have a full octet. It is not stable. So the less stable of the two is this one, is O by itself. It means it's more stable when it comes together. So that means we're going to have higher energy for the one that's less stable. We're going to draw that on top. And I'm hoping. So something like this, does that make sense? Our O2 is more stable, it's lower in energy. Our oxygen atoms, there's two of them, are up top. So how would we calculate delta H if we look at it like that? What would we be subtracting from what? How would those line up? Mathematically. Bueller.
When you do O2, subtract 2O.
So if we know that this delta HAC is negative 498 point whatever it was, what's delta H up here?
0.
And we have two of those, right? So the change, is it going to be a positive or a negative delta H for the reaction? For breaking bonds, is it positive or negative delta H? Are you guys just tired? Okay. So we're breaking bonds. It requires an input of energy, as Savannah was saying. Input of energy is going to be a positive delta H of a reaction. And that total change is going to be how much? And 0.32 kilojoules for every 1 mole of O2 that we're tearing apart. If we have 2 moles, we're going to require twice as much energy. 3 moles, 3 times as much energy. All right, what about the other one? I guess I had that all animated. That would have been easier. So if we use AL, we still have the same reactant, we still have the same product. What changes about our calculations? Josh? The values. Okay. So what's our value down here? What's delta H of formation is what they call it here? 0. And what's delta H of our oxygens? 249.2, I think. So the change in enthalpy of that reaction is identical. Remember last week I was talking about your 0 value. What's your 0 value? It's defined in Pogel book for delta AC. They define it as the individual atoms by themselves. In your homework and a lot of other places, they define 0 as the molecular compound. So then the individual atoms are going to be a positive delta H formation. So the thing I'm trying to get you guys to look at here is that regardless of what values you used, if you keep in mind the stoichiometry and you look at the relative value of your starting and ending products, you should, a very strong should, there's going to be exceptions probably with someone that has a wrong value posted, you should get the exact same change in enthalpy.
So is it just less stable minus more stable?
Well, I actually very much don't use a formula for less stable, more stable, because then you might get it mixed up, because if we're thinking about, if we're going from O2 to another, like through this to another product, well, then it's going to say, well, it's a positive delta H, going from reactants to products. Or it's a negative delta H, it's going from reactants to products. So I very much look at, first, do I expect it to be positive or negative, and then I find out what the difference is.
Is this the one that we'll use on the class stuff? The one you gave us?
I think that seems reasonable to give you on the test this guy. But regardless of what table you use, you should still get the same differences between reactants and products. Did I not answer your question in a good way, Joey?
I'm just trying to figure out how to put it in my own words to set it up.
Yeah, and I think that's the most important thing.
To be honest.
So you got a negative, you mean, or?
Yeah, I ended up doing O2 minus 2O.
Yeah, and so what's really important there with putting in your own words is going back and saying what direction is the reaction going? Is it going from more to less stable or less to more stable? And a lot of times you can't tell because there's two sets of reactants and products and you don't know. It's not just tearing them apart. So then you have to look at the actual values, draw out the diagram, and then say, well, we're going to lose more than we gain. We'll kind of go through that in some practice today. So for this first question, it absolutely does not matter which set of values you use. The really important thing is making sure we set it all up appropriately. Yeah, Kiana? So you can't mix and match. You can't use some values from your table and some values from their table. You have to stick with one set of values because the relative zero is going to be different. So you would either, I think some people are saying they Googled a table. Some people are saying that they use one that's in the book. You can go to the book and you can find a table for enthalpy of formation. And then you can't use this value and this value because then that's going to be totally out of whack. Yeah, Lenny?
So when I do my homework, because the table is given because the different sources of the table, so the result will be wrong. Then the percentage that I got, it will be less. So what you're gonna do with that? You have to, at some point, because it's not our mistake that we do not understand the concept. We did what we have to do, but the source itself is wrong.
So
you must compromise with that.
if we stick, whatever table you choose, if you do the process, then the answers will be correct.
No, because the answer is wrong, sir.
So we'll talk about it after class. I got the email that you said that you were having some disagreements with this, so I'd be happy to sit down and talk to you right after class about this, and then we can make sure that it's fair. Okay? All right, so our learning objectives for today is that I want you guys to be able to calculate delta H of a reaction, also shown as delta H, and I put the little RXN for reaction down here, in case you see me drawing shorthand, based on values in a table. That's what we're going to be doing a decent amount of. And then I really want you guys focusing on drawing the diagram, thinking about what's going to be more stable, the reactants of the product. Should delta H be positive or negative? How many of each reactant, how many of each product do we have? And then using that all to come up with an appropriate answer. And that's going to allow us to start thinking about the strength of bonds based off of the value of delta H of a reaction or of an individual reactant. So we're going to be spending a lot of time doing some calculations. Some of that's going to involve quantities as well. So let us think about a question that will set us up to go back to the POGO activity we're working on. We are going to finish that activity today. All right, guaranteed. You guys help me out with that? All right, I want you to think about, with some delta HAC values, I want you to think about which one of these bonds do you think is the longest and why. Go ahead and talk to your neighbor. Try to figure out which one of these is the longest. All right, a couple more seconds. All right, gonna go ahead and close out. That's why you're not assessed on correct or incorrect. All right, we have about 3-1 for answers. So one of the answers is wrong, one of them is correct. Can I get someone who talks with their group and thinks that they have a decent understanding of this to share their answer? And I think I'm going to do something starting today or tomorrow. Let's do next class, but I want us to start moving this way. I want everyone in class to speak once before the end of the semester. So you can kind of take your pick as you go forward when that is. I don't necessarily need to cold call on people, but let's start that next class. Or if you're very confident in answer today, you can give your answer today. You can email me to remind me, and I'll put a little tick by your name so that it'll count towards that if you really don't want to talk the rest of the semester. So I want to hear from a new voice. Which of these bonds is the longest, and how did we answer that way? Aaron, what are your thoughts? Great, so there's a lot of different things you said in there, and I agree with all of them. So this delta H value is negative, so that means that when those two atoms come together, they release energy. They release much less energy than the other ones. They release less energy because they form a less strong bond. That means it's easier to pull them apart, which is what Aaron said as well. Easier to pull apart because it requires only an input of 295 kilojoules per mole. And we talked a lot earlier in the semester, but it was kind of more like just a statement, right? Longer bonds are weaker, shorter bonds are stronger. We talked about that as well with single, double, triple bonds as well. The more bonds they are, the shorter they are, and the stronger they are. We didn't really talk about single bonds being different lengths. So this is where we can start to see that actually play out. So this HI bond is absolutely the weakest of those bonds. So then how does delta HAC, how does that compare if we were to say, what's the bond energy? Which one of these would have the strongest bond energy? Maybe HF. So the bond energy describes actually the way that Aaron said it. It's harder to pull those two apart. So it talks about how much energy needs to go in to break those apart. If we look at the length, this is the longest. Why might we have gotten the shortest bond wrong? Talk to your neighbor for a second. Why might we have guessed that B was the shortest bond, but it's actually A is the shortest of these two? What additional factor besides bond strength do we need to think about when we're thinking about bond length? All right, I'd like to hear from a new voice. So why is it that we might guess that HF is the shortest bond? And then what logic might we have that would actually allow us to guess that HH would be the shortest bond? Kevin?
Is it electronegativity?
Relates a little bit to that. What about it?
That H and H have the same, or both hydrogens have the same electronegativity, so it'd be like no difference.
So it's a nonpolar bond. This is true. But that's not quite about the bond length and strength, love.
The size of the atoms that at the bottom.
So which one is bigger, a fluorine or a hydrogen?
Fluorine is bigger. Hydrogen to hydrogen is just one photon to one proton, and the bond will be closer.
Great, so when we have two hydrogens separate, we bring them together, they don't release as much energy. It doesn't form as strong of a bond as when a hydrogen and fluorine come together. Right? This is a stronger bond out of the two. But when they form that stronger bond, fluorine has a larger radius. And so the atomic radius is slightly bigger, which means it can't get quite as close to the hydrogen. So then why, logically, is this the weakest bond? Dr. Neighbor, why is HI, thinking about the properties of the atom, why is that the weakest bond? I want to hear from the new group. All right, can I hear from a new voice? New voice, please. You volunteering here? All right.
Because I would be the largest atom that's on that list, because if you look at the rules that we talked about at the start of the year, it's further down, and then the rest of them end.
So the larger the pairing partner is, the less close hydrogen can get to it to form that covalent bond. And so the iodine is the largest atom, which means it can't get as close. Because it can't get as close, it's not going to form as tight of a bond. And so this is the weakest bond, longest bond, because it can't get as close to the hydrogen. All right, so that is also, you can refer to bond energy. What else changed when I changed that to bond energy? You guys notice anything else changed about the table? All the values are positive. So bond energy is how much energy it takes to rip them apart. Enthalpy of atomic combination is how much is released when they come together. All right, so go ahead and let's start working on activity 35 again, model 2. Critical thinking questions 10 and 11. If you finish those, start working on the exercises. I don't have any more copies, so if you forgot yours today, you'll have to share with someone else. So please move next to someone that has one if you do not have yours.
I wish this would. Oh, you guys, I've never been up here. Hey.
Scared me, actually just came down here. I was like,
No, right? Yeah, because y'all are like, I believe y'all got you. Holly, go to Look, where's everybody?
increasing bond strength. Bond strength. When it just be
Got your haircut.
Yeah, I did.
Christian, you need to do you have your coffee.
Yeah.
We do have basically been all that.
You like you though. You're looking really good. I'm not even doing Do you like fake socks? What type?
Do you have the appendix too?
So they're always 0 items.
But depending on which table you use. Like this table uses if there's a molecule, then like the I2 molecule is the molecule. Yeah. Instead of
Did anyone not have an appendix? You weren't here on Friday. By the way, we're gonna give a shout out to Jason. I'm a kid today.
Oh, congrats.
you not see it?
Is it Josh or April?
I'm assuming you're, yeah.
Since it's not charged.
I just gave out all the ones that I had, so you just
Oh my god.
It's HBR.
Nope. 11. Based on bond links, which one do you think will be stronger, CH or C? So we go looking for the table. It's by like, wow.
Yeah.
H to C.
What do you
But it's based on bond.
So is the last day. December 3rd.
Or whatever the first, we come back from Thanksgiving, and then we
feel
have
like
1 week,
because
and the
there's
next
more
Monday after that,
siblings,
week Thanksgiving.
My question is there a cost enough for them?
I don't think there is.
I think that would push it on. I'm gonna stick to my gut.
Alright, if you guys are not done with critical thinking question 10, please get moving. You should be almost done with question 11 by now, so keep working. We have less than 20 minutes, and we have a lot more exercises to do to make sure we're doing this. So I think people are confused because they want to make sure about conditions.
So if it's predicted impossible, it has to be like stronger or like the actual
Relative value. Greater or less. Delta H. Delta H bigger or smaller?
So it's asking which one's bigger or smaller, not like the actual.
Correct.
I saw a girl at my work yesterday, and she looks like she'd be your mom. Like I almost asked her, what's her birthday? No. Okay, she had the same demeanor as you. I don't know. Okay.
Which one? It was 1570. Right. My answer to part A was that
She's
the
calm.
value shows that because it requires. So that's not right. Okay. No, because they're closer together. It says C and H. Yeah, they're further apart because the one that's and the yellow is going to be a bigger.
How are you getting
Work on, then I work on.
So let's get together and talk through a little bit of critical thinking question 11. So question A says, based on bond length, which would you expect to be stronger, a CH or a CCl bond? Why'd you say CH, Gil?
Because they're closer together.
Why?
Because of the atomic radius of.
Okay, so you said CH would be a shorter bond because the atomic radius of hydrogen is smaller than chlorine.
Yeah.
Great. Does that mean it's a stronger bond? This question was specifically asking about strength.
I'm only saying to what I expect, and I expect it to be stronger.
Okay, great. You expect CH to be a stronger bond because it is a shorter bond, because of the atomic radius. Great. So then, if we use delta HAC for CH4 versus CH3Cl, how does that help us think about the relative strength of the CH versus the Cl bond? Can I get a volunteer to describe how that actually helps us? 11b. Can someone give me the delta H atomic combination for these two compounds?
CH4.
And then for the other one, it's negative 1,573.15.
Nice, you meant kilojoules. Alright, so we have these two values. How is this going to tell us anything about the relative strength of a CC versus a CH bond? Kyle?
The more energy it takes to put them together, the stronger the bond will be.
Takes to put them together?
Or to break them apart is very much stronger. And so because their enthalpy is...
I'm just going to tweak one thing you said. So the more energy is released putting them together. That's what I would have said, not it takes. Okay. Go ahead.
So since it releases more energy to put them together, it'll take more energy to break them apart, which makes it stronger.
And so what's the only difference between these two molecules? So one of the single bonds is between a carbon and a hydrogen versus a carbon and a chlorine. That means that all three of these are going to be the same energy as these three. Most likely, there's some nuances when you get into organic chemistry, that's not completely true. But for now, we're assuming that a CH bond is a CH bond. So that means that if we have 4 CH bonds, could you guys find the individual bond strength for one CH?
Yeah.
It's a quarter of this. Over here, if we know what it is for every CH bond, could you find the CCl bond strength? Or the delta H for that specific bond? Alright, so you could calculate it mathematically. You could also say, well, I know that forming these 4 bonds releases more energy than forming these 4 bonds. That means that this one must not release as much energy as this one. Either of those two is completely fine to describe how we're thinking about this. So then the last question, 11c, says, based on your delta HC values for CH4 and CH3Cl, predict delta HAC for CH3 with the fluorine or a bromine, and it wants relative values. Do we think that this, with the fluorine here, is going to have a bigger or a smaller change in energy? Is it going to be a stronger bond or a weaker bond if we have the fluorine or the bromine? Stronger with the fluorine? because it's a smaller atom, it's a stronger bond. It also has to do with this electronegativity or something that relates to this electronegativity. It has a stronger pull for those electrons, which is why it's more electronegative. So this one is going to pull itself closer, making a stronger bond with carbon, which means that the delta H AC value for CH3F is going to be more negative, maybe is a way of saying it. It's going to be a more extreme amount of energy released than bromine. Questions? All right, go ahead and do exercises. Actually, one question I have for you. Two things. One, thank you everyone for your service in here if you've been in the military or any part of our armed services. Never forget, I think is the phrase that's supposed to summarize that, right? Thank you. The second thing is I have office hours scheduled this afternoon from 3 to 4:30. Seeing as the campus is pretty quiet, I might shift those hours to some other time. Can I see a few hands raised if anyone was thinking about coming to my office hours this afternoon? One hand raised. Anyone else? So if you want to meet with me today, please email me right now. You can meet with me right after class, but I might shift. I might not have formal office hours. It might just be one-on-one meetings. So please email me, and I can see if I can find a time to meet with you. And then I might not be here during that time frame this afternoon. Okay? So let's go ahead and do exercises 1. As you do exercise 1, go ahead and draw out your enthalpy diagram. Right? If it's exothermic versus endothermic, I want you to draw out your reactants and products. You don't have to draw the whole thing, but I want you saying what's the relative enthalpy of atomic combination of reactants, what is it of products, is it endothermic, exothermic, come up with some values, all right?
What is the,
Why don't you go ahead and click in exercise 1A. Exercise 1A. So as you get that number, I want to know how you guys are progressing. We literally have 6-7 minutes left. We're going to get through these.
what is 1A?
Exercise. Once you're in exercises, question 1.
MgOH2.
If you are stuck or not completely confident, please raise your hand and Sam or I will come around and help.
I have the numbers if you want. For MgO, it's negative 998.57. And then for H2O, it's negative 970.3. What a cutie! And for MgOH2, it's going to be negative 2005. It's going to be exothermic. And it would be negative because Yeah. Okay.
All right, so let's go up here. Let's think about the first question. If you've added up the delta H AC for both of your reactants, what value do you find? (1,968.87 kilojoules per mole). That's our positive delta H for breaking all those apart. What is the release when we think about just MgOH2? Is that 1,000? I don't have the numbers in front of me because I gave away all my packets.
970.3.
Okay, so if it requires 1,968 kilojoules per mole, we release 2,005 kilojoules. Is it exothermic or endothermic? Exo. So that means that it would be this one here. MgO plus H2O liquid, right? Solid liquid yields MgOH2. Solid?
Well, it would be aqueous if you had an excess of water.
If we did, but I think it's stoichiometric conditions.
Okay.
So then our delta H for the reaction, how do we find that? So we find the difference between these two, and this is kind of what Joey was asking about earlier. Which do we subtract from which? I prefer not to do that. I say, well, what's the difference between them? If I draw out this diagram, then I know that it's supposed to be a negative delta H. Otherwise, you get stuck and you end up with a positive. You don't really know what that positive means. You don't know where that came from. So that delta H in this case is a negative, what does it end up being, 37 kilojoules per mole of MgOH2 formed, or per mole of MgOH consumed, or MgO, or per mole of water consumed. All right, so go ahead and do this for the next two. What's the only difference? So I'm looking at the clock.
2 minutes.
One thing, so let's look at part B. When we have 2 moles of zinc, what changes about our calculations? We have to, whatever the delta H of zinc would be, we multiply that by 2. What is it? It's 0 in this case, right?
Oh yeah, because it's an element. Same thing with the oxygen.
Oh, it's a solid, it's not the gas, you're right. So it's not 0. And then we have 2 of our zinc oxides. Is that endo or exothermic? If it's exothermic, negative delta H again. Okay? Before we end class, I think you guys can work through the rest of those. I want to ask one last question. This question, go down to problem 1. Work the rest of those as practice. Say again?
Melting sulfur dioxide. Yeah.
You guys will get to practice. We can do them during office hours. Go through them. Oh, okay. Last, we're not doing this as a clicker question. I want you guys to look up delta H for this physical reaction. Hopefully you guys have been paying attention to the states of matter. And you've seen there's different values for a solid, a liquid, and a gas. Can anyone tell me whether you expect this to be a positive or negative delta H for this physical reaction, physical change? Positive. Why would it be positive? Why do we not even need to look at the table to figure out this is positive? You take something from being more stable as a solid to less stable as a liquid. Now those particles are moving around past each other. How big is that difference? What's delta H there? delta H equals, what is it, 13? About 13 kilojoules per mole. What is it for liquid to gas? Does it take energy to take a liquid and make it into a gas? That requires an input of energy. It's a positive delta H. What requires more energy? Taking a solid to a liquid or a liquid to a gas?
Liquid to a gas.
That is not breaking apart any bonds. We're not rearranging any atoms between each other. We're taking two molecules and we're saying those molecules have some electrostatic interaction. We're moving them past each other now as a liquid, or now they're free to move around. I want you to be very careful to think about the energy required to change phases versus for a chemical reaction.
Oh, goodness.
All right, anything we didn't complete in model or activity 35 is on your own. Next class, we're going to start talking about biofuels and how this all plays out into climate change and transportation.
Great.